first law of thermodynamics is that the energy of the universe is constant. The way it's typically applied is that the heat lost to one object plus the heat gained by a second object is going to be equal to 0. Or in other words, heat lost and heat gained are opposite but equal values. Let's look at an application. In this example, hot water is added to cold water. The hot water is going to cool down, and the cool water is going to warm up, and they will both end up at the same temperature, TF. And the first law says that the heat lost by the hot water added to the heat gained by the cool water is equal to 0. The energy of the universe is constant. We're going to calculate the heat as mass times specific heat times delta T. However, in this instance, the mass and the change in temperature is different for the hot and cool water. So there's cool water, it's 50 grams, it starts at 30 degrees C, and there's 40 grams of hot water that starts at 90 degrees C. Again, we mix them together. The cool water is going to increase in temperature, the hot water is going to decrease in temperature, and they'll both end up at the same temperature, TF. So we're going to apply this equation to the hot water and to the cool water. Now, this is a lot of algebra. We're going to solve this equation for TF, the final temperature of the resulting mixture. Now I'm going to rewrite the equation ignoring units so that we can see things more clearly. Now I'm just going to step through the algebra solving for TF. I've used the distributive property 40 times TF and 40 times 90, and on this side 50 times TF, 50 times 30. Alright, so it's a lot of algebra for this problem. It is kind of a difficult problem. Here's the nut of it. There's hot water losing heat. There's cool water gaining heat. The sum of the heat lost and the heat gained equals 0. That's our first law. So applying this equation, we can step through and solve for the final temperature.